So it's a great honor for me to introduce Professor Eugene Dynkin, the Bullis Professor of Mathematics at Cornell University. He started his career very early, at an early age, when he introduced Dynkin's diagram in Gelfand Seminar. He used this diagram to study the automorphism and the subalgebra of real algebras. And at the same time, he started to work with Kolmogorov in probability theory, a subject that he pursued all his life. He actually, I know that he returned to Dynkin diagram in the last few years, and I'm sure he will tell us about that. He had many great accomplishments. Several results have his name. I will just mention the famous Dynkin isomorphism that describes the structure of Gaussian fields. In the last 20 years, he works mostly on super processes, terms that he helped coin. He received many honors. He is a member of the American Academy of Arts and Science, of the National Science Academy. He receives a Steele Prize for Life Achievement in Mathematics from the AMS. He's received a Doctor Honoris Causa diploma from the University of Paris 6, Pierre and Marie Curie, Warwick University, and the Independent University of Moscow. And I'm very happy to let him tell us about 70 years in mathematics.
Thank you. So, 70 years ago, at the age of 16, I was admitted to the Department of Mathematics of Moscow State University, and so I start count my life in mathematics from this event. First 36 years of these 70 years, I lived in the Soviet Union under rather oppressive political system, and in 1977, I moved to the United States, and I start my teaching at Cornell University. So it is 33 years as I am here at Cornell. Let me start from the beginning of my life, which was not very happy. At the age 11, I was 11 years old when my family was exiled from Leningrad, now St. Petersburg, to Kazakhstan after great purge of Leningrad, after assassination of Kiev. And in 1937, my father became one of millions of Stalin's victims. He was arrested and immediately shot without any trial. But his wife, my mother, was told that his sentence was 10 years without a right of send or receive any letters. And during Gorbachev's perestroika, we learned that this was euphemism for immediate killing of people. And there were, nobody published official figure, but at least hundreds of thousands, maybe millions. There were even quotas for every region, how many these people were called enemy of the people, and nobody, there was a quota how many such victims should be at any, in any region. It seemed almost a miracle that I was admitted in 1940 to Moscow University. Possibly it helped that the school teachers accelerated my graduation from the high school, so I graduated 1 year earlier, and they sent a letter to the Education Ministry asking to waive, in my case, a rule that the 70 was the minimal age for an admission. So this was granted. And as an applicant with all A grades in school, in the school diploma, I was interviewed by one of professors. There were entrance examinations, but for A students, they were waived and replaced by these interviews with one of professors. And it happened that my interviewer was quite prominent, eminent mathematician, Professor Alexander Gelfand, not Gelfand, Gelfand, who was internationally recognized because he solved one of Hilbert's problems. I brought a notebook with some formulae related to Bernoulli numbers, which I deduced myself. Of course, this was not really anything new, but probably I made a rather favorable impression on my interviewer, and I was admitted. Even there was a competition between students with A diplomas. I spent my freshman year at Moscow University. Then, in June 1941, the Hitler army invaded the Soviet Union. The university was evacuated, but I moved with my mother to Perm in Ural, and for 2 years I continued my undergraduate study at local university. At that time, the city was renamed Molotov instead of Perm. Now it is again Perm. Yes, and I was readmitted to Moscow University in fall 1943. So first of all, let me tell a few words about my freshman year, which was very important. So this was very happy occasion that I graduated from high school 1 year earlier. Otherwise, I could not have this very important jump start at a very stimulating atmosphere of Mehmat, Department of Mathematics of Moscow University. Especially important for my development were 2 lecture courses. One was course of algebra, mandatory course of algebra for freshmen, given by Israel Gelfand, who was very young at that time. He was 27. He just got his degree, and he impressed very much the audience, including myself, especially probably myself, because he presented linear algebra in spirit of functional analysis, which was something new at that time. All textbooks have been written in coordinate language. And he considered linear algebra as algebra of linear operator in finite dimensional Hilbert space. Coordinates were secondary. I remember my joy when I solved one problem given him at the lectures to prove that if two complex matrices commute, then they have a common eigenvector. Of course, it seems very trivial, but still at that time it was a great joy to discover this by myself. And the second course was a course by Kolmogorov. And this was a special course, and the audience consisted mostly of graduate students and senior undergraduate students. This was the course in set theory. Kolmogorov, in general, had a tendency to overestimate ability of his audience. So there was a saying that Kolmogorov's lectures for school students could be understood by university students, for undergraduates by graduates, and for graduates by professors. Not all, some professors. It was very hard for me, a freshman, to follow this course. But I was persistent. After every lecture, I read a corresponding chapter of monograph of Hausdorff set theory, and most of week I spent for this reading, so I was prepared to the next lecture this way. Even set theory was not in the center of my research later, but acquiring some culture in this respect was, of course, very beneficial. Now I go to my return to Moscow University after these 2 years in Perm. I was one of first participants of famous Gelfand Seminar, which started about that time in December of 1943, or maybe January 1944. There was a very small group of participants at that time. Of course, most people were either in the army or not in Moscow, so it was a very small group. At that time, Gelfand started to work on unitary, infinite-dimensional unitary linear representations of Lie groups, simple Lie groups in particular, and therefore the killing Cartan theory of simple and semi-simple Lie groups and algebras was in the central subject of the seminar at that time. Selim Crane and myself were requested to present this theory. My task was to present final, the most contemporary presentation of the last step of classification of simple Lie algebras done by van der Waarden. I was not able to understand rather complicated computations with determinants in van der Waarden paper, so I instead went by my own way, and I will tell about this a little. So, simple Lie algebras which characterize the corresponding Lie groups up to local isomorphism consist of 4 classical series and 5 exceptional algebras. And the structure of all these algebras is described in terms of root systems. And a root system is simply a finite set of vectors in a Euclidean space, if you want. And the structure formula, commutators of any 2 elements of a base as a linear combination of the base, is described, can be described in terms of this root system. But root systems are rather complicated, especially in the case of exceptional groups. I mention here that in the case of E8, where is oh, here it is. Okay, so in the case of E8, this system consists of 278 roots, which cannot be described in any simple way. So to work with such kind of finite set is not a simple thing to do. Of course, instead, we consider what we consider instead is a base of this system, just 8 vectors, and all 278 can be represented as linear combination of these 8 elements of the base. But the idea which came to my mind is to choose this base in a special way, namely to consider simple roots, which means vectors which cannot be represented, decomposed into the sum of 2 roots. And it turned out, and this was a new idea, in fact. Bases used by van der Waarden and other people before were just described for each case separately without any general approach. And it turns out that pairs of simple roots could make only the following angles. First of all these angles are obtuse, and only these 4 values are possible. And this can be represented by diagrams, 90-degree, just two dots without no connection. The second case, one bond. Here we have double bond, and here I suggest to use triple bond. And if you apply this simple observation, you arrive at the following picture. First of all, let me explain the top of this. So for the case when base consists of two elements, all root system can be, of course, presented explicitly, and it is right here for A2, B2, G2. But for all other cases, you cannot draw pictures easily for entire root system. But using this observation, you can draw diagrams, and people call it Dynkin diagrams. For some, I should, by the way, mention when I left of the Soviet Union, this was considered a kind of bad thing, treason, and I was told by people who came after me here that the name of Dynkin was excluded, and it was requested that this diagram would be called diagram of simple roots. Later, of course, this was changed. Now I, of course, have no time to present in detail various applications of these diagrams, but I can briefly tell this. 4 directions. Irreducible linear representations can be described by one of these diagrams. Say, if you speak about representations of, where is E8? For instance, if you are interested in the representation of F4, you assign to every vertex a number, an integer, positive integer, or 0. These numbers are different. This is simply for a reference. But you can write any, for instance, you can write 100, 0 usually just skipped, say 1, 4. And this is one characterization of one of irreducible of linear representation, which is a very convenient way to consider them. Now, important direction is describing of subalgebras of an algebra. In the case of simple algebra, we consider subalgebra which are either simple or the direct sum of simple, which are called semi-simple. And classification of subalgebras, which is the main step in classification of Lie subgroups of a Lie group, and the last letter is equivalent to classification of transformation groups. This was a classical problem started by Sophus Lie himself, how to describe all primitive transformation groups. And this machinery helped very much. And this was my second dissertation, description of all semi-simple Lie algebras of simple Lie algebra, which led to classification of transformation groups. Now, this was, when I came to the United States, I discovered, which I did not know, that these my results are used by physicists to build unified models for description 3 or 4 basic interaction types, namely electromagnetic, weak, and strong. Only gravitation is left in these models, and to cover gravitation, more recently, they use the spring theory. But in 1960s, this building of these models was one of important directions in particle physics. Gelfand got a Nobel Prize for this. This is taken from a book called Group Theory for Unified Model Buildings, written by a physicist Slansky and published by Livermore Atomic National Laboratory. And now, one more direction of future research, we're investigating of nilpotent orbits, which means that we are interested in the Lie algebra in classes of nilpotent elements, which means in group language, power is equal to 1. In algebra language means that power is equal to 0. And this classification of nilpotent orbits is a substantial part of theory of infinite-dimensional linear representations of Lie groups. So these are some of directions where these diagrams were used very much. Next, I will speak about the second seminar which I participated in as an undergraduate student. And this was 1944-45 academic years, and this was Kolmogorov's seminar on Markov chains. Kolmogorov posed, among various other problems, a problem which is on the border of theory of Markov chains and linear algebra. namely description of eigenvalues of n by n matrices with positive, non-negative entries. It is easy, can be reduced easily to the case when the sum of elements in every row is equal to 1, and then these are stochastic metrics which describe transitions in a Markov chain. And eigenvalues are important because asymptotic behavior of powers, which is the same as behavior of trajectory of Markov chain, depends on these eigenvalues. So the problem was as following. Consider all stochastic matrices of order n by n, and all their eigenvalues. What figure on complex plane you get? The final answer, okay, so this is the final result about this. So we have a figure in the plane, of course, complex plane, but all these sets are contained in a unit circle because all eigenvalues such a matrix are in absolute values smaller than or equal to 1. And the first problem was to show that they are in the angle which indicated here by blue lines, because this actually what was important from the point of view of asymptotic behavior of Markov chain. So this problem, this part of the problem was solved simultaneously, independently by Kolya Dmitriev and myself. Kolya Dmitriev was my was a student in the same class as myself, and later he got some prominence in connection with creation Soviet atomic bomb, in particular even hydrogen bomb. In his memoirs, Sakharov mentioned him as a mathematician who was able to solve every problem which they have needed to be solved. So we independently got this result, but I suggested a very simple approach to this, geometric approach, namely complex lambda. If you have a lambda, then it is an eigenvalue of matrix of order not bigger than n, if and only if there exists a polygon with number of vertices not bigger than n, such that is transformed into its part under multiplication by lambda, which geometrically means, of course, rotation on the argument, and dilation or contraction is absolute value of lambda. So the problem was reduced to simple geometry of polygons, and I was able to get the complete description of this figure up to some n, but not completely. Later, my student, very talented student, Karpilevich, finished and got the complete solution, which is presented here, but you can, I would not go into detail of this picture. You just see that it is rather attractive by itself. Okay. Now let me proceed. In March 1948, I defended my PhD dissertation, which contained an explicit form of Campbell-Hausdorff formula, which I just, to explain what is this, I just demonstrate one page from Wikipedia. So this is about construction of Lie group starting from Lie algebra. And it is constructed in the following way, by using this series for logarithm e to the power x, e to the power y. X and y do not commute. And what is needed to express a formal expression of this series in terms of commutators, which means xy minus yx, and polynomials, commutator of two polynomials is defined the same way. And here it is explained who are people whose names are mentioned in the title. And the last one, Eugene Borisovich Dynkin is a Russian mathematician. Which only partially true, because we say Afro-American, so probably I should be called Russian-American mathematician. And also, they used Russian way with patronymic, but in this case, I should be called Evgeny Borisovich, not Eugene Borisovich. So this is a mix. So let me proceed. What was my contribution? I simply discovered that you get expression of this series in terms of commutators if you take every monomial and replace all multiplications by commutators and divide this monomial by its degree. And this can be demonstrated on example first, this is linear, quadratic, cubic part. So in the case of Z2, you have very simple expression as commutator. In the case of Z3, this is an exercise for high school algebra, I suppose, just to check that this is equal to this, if you consider each commutator as the difference of two products in two orders. Now, the next, what I want to talk about is my gradual move to probability theory. In 1948, but I'm afraid that I need to be concerned about timing. In 1948, after defending my PhD thesis, Kolmogorov wanted me to be appointed at Moscow University in the Department of Mathematics. To this end, I defended my thesis earlier than it was necessary, in 2 years and a half. And there was some vote of faculty meetings, a so-called competition, and I passed this appointment by this rather unanimous vote. However, despite, according to law, this would be sufficient, a committee responsible for assigning jobs after to every after graduating sent me to Pedagogical Institute, Provincial Pedagogical Institute in Vitebsk. So Kolmogorov put all his regalia, hero of socialist trade, Lenin orders, etc., 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 went to ministry, and he succeeded that they capitulated, and I was appointed. Now, starting 1955, the main subject of my research became Markov processes and related problems of analysis. In this relation, I would cite one of leading French probabilists, Paul-André Meyer, who said that the general theory of Markov processes, this was acme of it in 1955, 66, during this decade. And I even am going to show a citation from his paper, published in 1997. Let me read it, but you probably can read it yourself. So I'm not sure that I need to read it. I mean, you can read it, and I will prepare the next slide meanwhile. So, I am going to explain what is a Markov process, what was my 1955-56 contribution to this theory, which was a start of my progress in this field, and what was the contribution of participants of my seminar, which is mentioned in this citation. So what is a Markov process? I start with examples. A random walk. Everybody probably has an idea. You toss a coin. With equal probability, you move to the left or to the right, and this is one-dimensional simple random walk. And obviously you can consider a random walk in 2 dimensions or in n dimensions. Now, if you move by very small steps and very fast, so time of each step is also small, under certain relation between these two constants, passing to the limit, you arrive at the Brownian motion. So we can say that the Brownian motion could be viewed as a random walk with infinitesimal steps, which takes infinitesimal time each. But this, of course, is not a rigorous expression. Now, we can consider a random path, which means paths of the Brownian motion are continuous. It can be started from any x. Xc sub t is position at time t, and you have something like that, but very irregular path. And we have a measure in the path space, which is I denote px, which depends on initial point x. A simpler description is by transition function, probability starting from x to b inside b at time t. It turns out that if you consider a function f along the path, and if you take integral of its value at point c sub t with respect to measure px, px, you have a function ut, which is a solution of parabolic equation, and A is called infinitesimal generator and can be obtained by this passage to the limit. And in the case of the Brownian motion, this is just 1/2 of the Laplacian, and therefore this equation is the heat equation. Also, what is important, the following property of the Brownian motion and random walk, namely Markov property, which is as follows. If you know position at time t, then forecast of future developments is independent on any information about the past. Past and future are independent if you know present position. It is clear that this property holds for random walk, and therefore it holds for the Brownian motion. And so I explained if we have measured in the space of paths with Markov property, then this is a Markov process. Now, what was my contribution? Two important observations. First, that instead of passage to the limit in time, it is possible to consider the corresponding passage to the limit in space. Namely, consider any neighborhood of point x, consider the path up to the first exit. Let me use this. So we consider, we start at point x, we consider the path up to the first exit at time, which I denote tau u. U is the neighborhood of x. And then you take integral mean value, you subtract the value at x, and you divide by mean value of the exit time, tau u. And if u is contracting to x, and then in the limit, you have what I call characteristic operator. And the result is that this characteristic operator is an extension of infinitesimal operator for every right continuous Markov-Feller process. Right continuous, it means paths are continuous from the right. Markov, I explained what it means. And Feller means, and intuitively, that the probability distribution at time t, if you start from 2 points which are close, are also close. So continuous dependence on initial state of the distribution at every fixed time t. So this was the theorem, first theorem. And second theorem was that every process with this property, this abbreviation means right continuous Markov-Feller process, has strong Markov property. What is strong Markov property? This means independence of future from the past, given not position at a fixed time, but given a position at a random stopping time, like first exit time from the domain. So these two results, introducing characteristic operator and proving for a large class of processes strong Markov property. The second one was in joint paper with Yushkevich. This was the main contribution at that time with many applications in future. It seems that I almost exhausted my time. It's very strange. Okay. No, anyway, I can, of course, present things shorter. So, I wanted to say about contributions of members of the seminar, but I probably have no time to describe it in detail. I only mention that this was a substantial part of my 2-volume monograph, Markov Processes, published in English by Springer and in Russian 2 years before. And it was also the subject of my plenary talk at International Congress of Mathematicians in Stockholm in 1962. Of course, I was not permitted to come to Stockholm and to give this talk, so I asked Kolmogorov to do this for my behalf, which he has done, but I sent a text which was published in Proceedings of the Congress. Now let me briefly describe my work between 1960 and 1976. Maybe I should mention intrinsic topology related to every Markov process. Because of topology, topological festival, maybe it is nice for me to mention something about topology. So if you have a Markov process, of course topology is defined if you define the collection, the class of open sets. So a set is declared open if starting from any point of this set, the trajectory stay in this domain with positive time, for positive time with probability 1. So if you cannot exit from this domain at once, it takes positive time with probability 1. And this topology is very useful because it turns out that in this topology, this failure property holds for very wide important class of processes, which I call standard processes first. Secondly, also, we can say that this definition is equivalent to the following property. A real valued measurable global say function is continuous in this topology if it is a right continuous along every path. And also, the next direction was application of Martin boundary to asymptotic behavior of paths. Here I mentioned just two problems. One is the Brownian motion in symmetric spaces. I consider as an example space of ellipsoids, or which is the same as the space of positive definite n by n matrices. So this space, we consider all ellipsoids with center, fixed center at the origin and fixed volume. This is a space which is invariant with respect to rotations, of course, and also with respect to linear operators with determinant 1 to preserve the volume. And the Brownian motion is continuous process with invariance property with respect to this group transformation group. So Martin boundary means that you consider this space, which is not compact, of course, and you embed it into a compact space in a special way. And what you add is called Martin boundary. And what is important from a probabilistic point of view, that the limit behavior of the path can be described in terms every path, almost every path, enters a certain point of this Martin boundary. And this point is, in terms of this exit point, you can describe all events which are determined by asymptotic behavior, which means you can change your path in an arbitrary way up to exit from some compact, and still this event will not be violated. And so evaluation of Martin boundary leads, for this particular case, leads to understanding the behavior, asymptotic behavior of this ellipsoid. You can try to guess what will happen with probability 1 with this ellipsoid. Its center is fixed, its volume is fixed, but what is the limit position, limit result? Now I can tell you that direction of semi-axis, of course, are also random, but they tend to a certain limit, and the distribution of this limit values for this repair can be evaluated. But what happens with the length of this semi-axis? No, in fact, it is written here, the answer. It turns out that we have 3 semi-axes. The biggest one tends to infinity. The smallest one, which is in our case, so we have the following thing. This ratio tends to 0, and therefore the smallest tends to 0. which means that your ellipsoid in the limit become flat. It is just a stripe. And the median length will fluctuate, but it does not tend to 0 and does not tend to infinity. It remains bounded. And another application of this theory, boundary value problem with oblique derivative. Now, we consider, say, Laplace equation. We consider the boundary condition that the solution derivative in the direction of certain field, vector field on the boundary is equal to 0. And we are interested in what conditions, boundary conditions, should be additionally given at points where this field becomes tangent to one. And it turns that we can get the result, analytic result about these boundary values by understanding what happens with the path. And here is explanation. 3 possibilities. If suppose that we condition suppose we have the following, the following 4 cases, 4 possibilities. Trajectory enters a point of the boundary from inside. It hit the boundary many times close to this point. So this final point is limit point for hitting point before. It could be from the left, it could be from the right, it could be from both sides. So it turns out that the first and the fourth possibility have probability 0, and 2 and 3 have positive probability, and therefore for instance, in such a figure, you can understand in which boundary point you need to give boundary condition and in which you don't need to do this. Now, because of time limitation, I would be very short about my research here at Cornell. Also, I suppose that people had more opportunities to become acquainted with this part of my activities. So I just mentioned 3 directions of research during these 33 years. Oh, yes, 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 of course. Markov processes as a tool in theory of random fields. This was inspired by quantum field theory, and this was one of main directions. Second, super Brownian motion and its application to semi-linear partial differential equations. Brownian motion is very useful to investigate Laplace equation and the linear equation related to Laplace equation, to Laplace operator. But if you have nonlinearity, this does not work, but instead you can consider super Brownian motion. And what is super Brownian motion? Instead of one Brownian particle, you consider a cloud of such particles. And each particle moves according to the Brownian motion, but it dies at random time, and at the death time, it produces offspring, random offspring. Could be 0, childless, 1, 2, 3, 4, etc., with given probabilities. So this is called branching Brownian particle system. Now, by passing to the limit, as the Brownian motion can be obtained from random walks by a passage to the limit, super Brownian motion also can be obtained by a passage to the limit from branching Brownian particle systems. To this end, you need to increase the number of particles, to ascribe very small mass to each particle, and to make lifetime, mean lifetime, very small. Then in the limit, you have measure trajectories in the space of measures. This is a measure-valued process. Instead of stochastic process, evolution of a point, which is a Brownian motion, we have evolution of a random cloud, or in other words, evolution of a measure. So this is a measure-valued process. And it turns out that you can write a solution of the Dirichlet problem for some semi-linear equations by using this super Brownian motion. Namely, the picture is as follows. I have lost this, but I find it. Yes, here it is. You consider, there is a general theory, but I demonstrate it on an example. Consider equation delta u is equal to u to the power alpha, where alpha bigger than 1. If alpha is equal to 1, of course, this is a linear equation, and everything is simple. But if it is bigger than 1, then you can write a solution as follows. You have a solution of the Dirichlet problem, which means a function f is given on the boundary of the domain. And we want to write a solution of the equation written here with boundary value the same as here. So to this end, you integrate function f with respect to the exit measure, and you take exponential with minus, and then take integral, and then compensate it by taking minus logarithm. And this is some new result, counterpart to much simpler formula for linear case, when you simply take the value of f at this point and integrate with respect to measure in the space of path. And so this was the first direction. And second direction was the description of all positive solutions of this nonlinear equation. The description of all positive solution of a Laplace equation, in other words, harmonic functions in the domain, is a classical part of potential theory, very well known. And the result about positive solutions of all of this nonlinear equation is much more difficult, and it is as follows. Positive harmonic functions in a domain are described by measures on the boundary. Namely, there is Poisson kernel. You integrate Poisson kernel with respect to measure on the boundary, you get your harmonic function. Here, you have several steps. First, you consider moderate solutions, which are solutions which are dominated by harmonic function. For these solutions, you consider minimal harmonic functions, which is a measurand for your U, and you take its trace, this measure nu on the boundary. Now, next step is to consider sigma moderate solutions, which means solutions which are limits of monotone increasing sequence of moderate solutions. And for sigma moderate solution, you still can describe solution, characterize solution by a trace on the boundary, but trace consists of a set gamma, which is a set of all x, where function u, a solution u, grows very rapidly. And nu is a measure on the complementary set. So this was a result of several series of papers. Most of them, many of them joined with Sergei Kuznetsov, who was my collaborator in this field for many years. I have written a monograph with presentation of this result, published in the colloquium series of the American Mathematical Society. But the end was an epilogue where main question was stated, which remained open. We know the description of all sigma moderate solutions. We do not know if there exist solutions which are not sigma moderate, which cannot be represented as limits of increasing sequence of solutions dominated by harmonic functions. So this question was open. And in a couple of years, a graduate student of Legal, one of the most brilliant French probabilists, the name of this young fellow is Selati, was able to prove that all solutions are sigma moderate, which was, of course, a great satisfaction for myself. And this way, the problem was solved completely by joint efforts, by contribution also of this young fellow, who, by the way, after that, decided to become a banker. I don't know how successful he is with the present situation, but definitely he was paid many times more than the academic people. So this is more or less what I have to say about my research. I don't know if you have a few minutes. I'm not sure that I have, but let us say that you can leave, if you want, And if you do not lift, I will demonstrate you some pictures. Consider this as not mandatory part of the talk, and tell a little bit about advantages and disadvantages to be a professor of Moscow University comparatively to be a professor of Cornell University.